Hello and welcome to Engineering 102 21B, Workshop B6, the COVID edition. So right now you're going to be doing your quiz online as you're doing your assignments. So let's pop over to our screen. So when you're doing this, we're now using the 102B Moodle site. You'll notice down here I've got Zoom tutorials. I'll have down here the Zoom. Your Zoom workshop is down under this tab, Online Workshops and Tutorials. It's Workshop 6. That'll be open from about 10 AM tomorrow morning when you're meant to be doing your class. It will be open for 2 hours. And just like an ordinary workshop problem, there will be 5 questions and you have to get 3 of them right for full marks. So, yeah. For those who haven't done their tutorials yet, there's their tutorial access through those Zoom sites there. But let's go back and talk to what we're talking about now. And what we're talking about is, for this workshop, what we're talking about is optimization. And optimization is one of the things that engineers actually do. I mean, one of our jobs is, what is the job of an engineer? The engineer is to build stuff faster, cheaper, with less materials than the average person, and also that it should be safer and meet all of the legal requirements and all the legal codes. So one of the things that we need to do is optimization. And some of you will have explored this in 101 to a small degree. We're going to take it a bit further. So some systems, what we do is when we optimize it, sorry for my draftsmanship, I'm having to use a mouse as a pen on this. One way is if we know we've got an equation, say the cost of a product that way, and we know this is the money that we make, or this is the demand curve, we can try and optimize to make the maximum profit. So that's one thing. And sometimes we can do this using simultaneous equations. Another technique that we use is we use min-max and use differentiation, as we've been teaching you. So let's say, and what we're going to be doing is we end up doing more complex examples. So my classic example is I do car tires, because that's my PhD was on suspension. We've got a car tire and we've got a spring. So that's attached to the car body. And in here, we also have a damper. Now, so this is a typical car suspension system. It's got a wheel, and the wheel is on the ground. And as the ground goes up and down, the car body here goes up and down in response. And the motion hopefully is stopped or slowed down by this damper. So when you're doing a damper, there's actually 3 different criteria that we look at. So when we're looking at dampers, what we need is ride comfort. Ride comfort. So that's when you're sitting inside a car, how much road noise actually gets through the car, how much shaking do you get through the car. Another one that's really important is road contact. The longer that your car tire is in contact with the ground, the safer you'll be. That makes it better for cornering, it makes it better for braking, acceleration. And the third one is rattle space. How much physical room does your car suspension use? So when you hit a bump, how much does it go up? Does the tire go up and down? That relates to how high it goes into. And with a traditional damping system, these 3 are mutually exclusive. You can have 2 of them, but you can't have all 3 of them. So, well, some of them you'll only have 1. So when you're talking about a sports car, like a little MR2 or a Porsche or a Ferrari, then the road contact is optimized. So the wheel sticks to the ground. When you're talking something like a Rolls Royce, then the ride comfort is optimized. and there's always going to be a compromise on rattle space. So we can set up this. If we want to do this, we can actually draw this as graphs. So hold on, let's go back to my draw instrument. So if I'm doing a graph, I can set up ride comfort, ride contact, and then or actually rattle space, and then I can try and find out, repeat this for comfort. Sorry, what have we got? Contact equals 0.2, contact equals 0.4. Now, we can plot these on a graph. So I might have optimal rattle space. So this is rattle space. This is ride comfort, sorry. Ride comfort. You might draw another graph in here. This is going to be, this would be contact. And we'll draw a third line in here. This will be rattle space. And you'll notice that these don't necessarily, it's hard to pull out an individual one, so you can pull out. So sometimes you'll have to make a compromise and choose this point here because it'll have best contact. And sometimes you might have to go lower because you can say we're going to go this. So what we're actually looking for is mathematical means to determine the best solutions here. And that's often we use mathematics and we use derivatives. We use minima, maxima to find out those solutions. And so what we do is when we have a problem, we try and stick everything as a value of x, or we try and put terms of everything into value of x. Later on next year, you might be able to put, when you learn multivariable calculus, you'll be able to put terms of x, y, and z. But at the moment, you try and stick everything in terms of x cubed plus 2x minus 4. And then what you do is you take the first derivative of that and 3 plus 2. And what you do is you make that equal to 0, and that will let you find out the values you're after. So let's actually take an example. We'll take a really simple example of the type of thing. But the whole point is doing this mathematically. The idea is we optimize by looking for the critical points. Because if we take the first derivative, we might end up with something like this. This is a maximum, this is a value. This might be in the range of what we can build, or the range of the rattle space that I was talking about before. So we can choose maximum values and minimum values inside that range. So anyway, let's go and apply this to a really simple problem. This is so simple. I used to give this level 2, level 3 at high school. Okay, so let's say we have, let's say the problem is I have a stream. Now I want to fence off an area around that stream using rectangular fence. Notice here, this is meant to be rectangular, so these are meant to be right angles. Everything's meant to be right angles here. So if I have L is equal to 500 meters, I've got 500 meters of fencing. What's the max using this rectangle? And remember, I can make it a narrow rectangle or a long rectangle. What's the maximum area that I can surround with that fence? So what's the biggest area in here that I can make? So what we're going to do is we look at this and we go, let's go back for green color green. Okay, so we're going to say this is x, this length is x, this length is also x. And this length here is going to be 500 meters minus both of these bits, so minus 2x. So now we can know that the area, the map, is going to equal, well, it's going to be this dimension, x, times 500 minus 2x. Now, so area is equal, if we expand that out, that means the area is equal to 500x minus 2, minus 2, yep. Seems right. Minus 2x minus 2x squared. Because remember, x times 2x is 2x squared. So now we've got the formula for the area that's totally in terms of x. So now what we do is, if this is f of x equals the area, which is, we take the derivative of that, equals 500 minus 2, take the derivative, 4x. Getting a bit carried away there. So it's going to be 4x. Now we have a derivative. Now, when this is optimum, when this is actually optimum, then that's going to equal 0. That's where it's going to be maxima or minima. So what we can then do is we just go 500. I just rearrange the equation, so all x's are on one side, all the everything that's not x is on the other side. Divide both sides by 4. So x is equal to 125 meters. And if another way we could have worked this out is I could have just stuck this into an Excel graph. I could have plotted this on this axis. I could have plotted x times 500 minus 2x. Could do this in a Excel graph. I plot x down here. So this is going to be the area. This is equal. And if you plot that, you end up with a nice upside down parabola, which is, it goes from 0 to 250, and the highest point will be 125. So it's nice to cross-check that our math actually works. But this is a really simple optimization problem. But we use, or have used over the years, this type of mathematics, this type of solution for optimizing all sorts of things. Because remember, if you're building a bridge nowadays, you want to use the least reasonable amount of materials, put in the safety factor, of course, that you can. I mean, if I'm going to build a bridge across a stream, any yobbo can make it, get 10,000 tons of concrete, make a simple beam and stick it across. But there's our stream. What about if we put a nice little arch bridge across there, and that weighs 1,000 tons? Isn't that lovely? And then I can give it eyes. That's pirate. Arr. Okay, but anyway, the point is that this one costs 10,000. He used 10,000 tons of concrete. This one uses 1,000 tons, and that's because of better design and using this type of stuff. So anyway, you have some problems. You've got 5 problems to do in the workshop. So yeah, good luck on that, and hopefully we'll see you in person next term in about 2-3 weeks from now. Okay, so good luck everyone, and yeah, if we can, let's hope we all have a good break.